Okay, so we continue our categorization of layers. We've covered the idea of weight multiplication and activation. These two, weight multiplication is the fundamental layer, and actually these two types of layers, weight multiplication plus activation, constructs the fundamental block in a neural network, which is the convolutional block or the fully connected block, whatever. Then we have the sampling layers, which is fairly a new idea because before convolutional neural networks, we did not come across sampling layers much in conventional artificial neural network design. However, we had in AlexNet, and what we had was the famous max pool, remember? The idea of these layers was to change these input layer dimensions. So sample them, downsample them, or upsample them. So you know what downsampling and upsampling is? Again, some concepts inherited from signal processing. You have a signal, you're changing the spatial dimensions. So what sampling layer does is it changes the spatial dimensions, not the depth. The depth was changed by one convolution layer, remember, in the previous hour. So downsampling an image by 2 makes it, if it is an n square spatial dimension, or n by 1 single line signal, like a sound signal, makes it a half dimension, n over 2. And upsampling by 2 makes it the double, like 2 times n nodes. Simple, in 1 dimension. So when you're defining a sampling, actually you define it in 2 dimensions. You may want to make a dimension and 2 times larger while you're making the other dimension, which is presumably orthogonal, which is independent, 3 times larger. It depends on your design. Usually, since images in vision has square pixels, the upsampling and downsampling dimensionality that increase or decrease is the same, so it's symmetrical. However, this does not necessarily have to be the case. Imagine you have a signal which is this was the same example I've given you. So people coming from our department, MMI, my department, this is a DI course, but MMI, who has taken signal processing in multimedia course will know what I'm talking about. For example, a spectrogram, or if you're coming from an engineering background, you also know this. A spectrogram is a frequency time image of a signal. For example, there's an earthquake signal. That's the frequency time image. In this case, when you're downsampling or upsampling it, you may want to apply different values to each dimension because the pixels of a spectrogram is not necessarily square, because one dimension is about time, the other dimension is about frequency, which are kind of not directly related. So it depends on the type of signal, how you are going to do it. But whatever you do, the sampling layers do sampling on the spatial dimensions, not the depth. Okay. Sorry. Sonra hocam şu an yanıma geldi. Ben sana vereyim dersten sonra. Olmaz. Hocam şu anda bırakamam. Hadi koş. Tamam, bir tane nefes alacaksın. Ne alacaksın? Tamam, al bir tane. I'm really sorry about that. It happens a lot when you're homeschooling. Anyways, what I was saying is, so it's in the spatial dimensions. Okay. So what you seen was in AlexNet the max pool layer, right? You remember in AlexNet, what you did was a 3x3 max pooling layer with stride 2, which meant you had a 3x3 layer. So this is a 2x2 max pool layer with 2. What you had in AlexNet was something like this. Let me try to draw it with my broken pen. So it was something like you had an image. Sorry, you had an image. Please draw an image. This is the channel. This is the input channel, which is in this case like this. Sorry. So it goes on 27 by 27. So what you had was a 3x3 max pool layer, which means you were selecting the maximum value from a region which is 3x3. Okay, you selected the maximum of this region. Then you jumped by 2. We didn't do any padding, you can see. Jump by 2. So the next square you have taken the maximum value of was, if this is the center, I jumped not by 1 but 2. The next point was this. So this is simply max pooling of this layer, defined as this. You get the maximum value. The type of pooling will depend on the type of operation you want to make. So max pooling makes sense for a classification network because we were trying to pick the neuron in this region, in this 3x3 region in AlexNet, where the strongest stimuli came from. So it was like we are trying to pick the strongest feature from there. Because what we want to say is not to exactly localize where the stimuli come. We're trying to get if any type of stimuli is there. If you have taken the average, you would lose a strong signal among some weak signals because you would be averaging it. But if you're taking the maximum, you are trying to understand how there is in that region, there's a strong signal coming in this feature channel, which is the feature channel, for example, in the deep layers that detects faces, which means there's a face in that part. If there's a face in some part, if there's something else in that part, you would say that, this is a, I don't know, some playground image, children's faces and blah, blah. That was the idea. Downsample by selecting the maximum value. Depending on your design, depending on your architecture, depending on the type of the information flow that you want to design with a specific purpose in your architecture, the type of sampling may change. You may need an average pooling. Okay, maybe you want to understand the average pooling or max pooling, I don't know. And there's also the unpool that I'm going to talk about. So this was max pooling. And remember, before I continue the other types, the output value of a sampling layer was calculated no different than a convolutional layer, the same formula. So in this case, it is 27 here. Let me use my pen again. So this is for, I'm doing this for this layer. 27 minus 3 minus no padding. Stride is 2 plus 1. So it makes 24 over 2, 12 plus 1, 13, which is 13. It is calculated no different than a convolutional layer, the same formula, okay? Okay, so, sorry, let me go on my slides. Okay, so downsampling. So the average pool is what you do by averaging. So in this slide, I forgot to put the square, sorry about that. So you downsample by averaging. There are types of networks that you may use this. You may have to use this, but it's simple. Okay, especially when you're trying to understand the total power of that feature coming from that region, not the existence of that feature, but the total power, then you would get the average. Why would you need the total power instead of the existence? Well, if it is not a classification network, if you are trying to get a value out of it, for example, if it's a regression network, trying to get a value, maybe it may be possible, useful to use an average pooling. Depends on your information flow and your design of how information flows in your network. And there's this famous unpool, which is a way of upsampling. So imagine you've done pooling, you've done max pooling here, right? Max pooling. You've selected 45. So in this part, I don't know, this is not max pooling. This is something absolute max pooling, maybe. Max absolute pooling. I don't know what this is. This is absolute max pooling, race. Absolute max pooling. It takes the value with the absolute max, the maximum absolute value of these features. Then, sorry, at some later stage, you are going to increase this to this resolution. What you want to do is you want to put these to exact locations, because I could upsample it by putting it to all values, because let me get my pen again. So it was like I've selected to put it here. So I'm going to, so this was 4 by 4. It became 2 by 2. When I'm doing unpooling, which is upsampling, I'm going to get a 4 by 4 again, but this is 2 by 2. I will need some sort of interpolation. So what am I going to do? Am I going to put this 0.45 value to all these cells? I may do it. However, I may choose to use the exact location of this value, looking at the previous layers to where they came from. To be able to do this, I would need to pass the indices of the previous layer to this layer so that I will not lose the localization of this feature. So, okay, I selected the strongest absolute value of that neuron, of that part. However, I don't want to lose the location as well. So this is an upsampling layer with index info. As you can see, I've designed an upsampling layer. Now, in this example, it is designed. In such, the information flow is designed such that the index value that the absolute maximum value comes from is also passed. So it's a different type of a network. Actually, this is a very common design as well. This is an idea taken from a very famous network, which is called the UNet and the SegNet. In SegNet, it is not exactly like this. The indices are passed in SegNet. It's also a semantic segmentation network. And these are being used widely in semantic segmentation networks, which we are going to cover today in the practicum session by the end of the lecture. But okay, so I understand that we can pass that information, but how to pass that information? Actually, you need a special sort of layer for that, which is the combination layer or the concatenation layer, where I'm passing this information from here to here, right? So I'm pulling, I'm passing this information, in this information from here to here. How to do it? We need these concatenation, combination layers for that. Okay, combinations layers combine or split output of a layer to another layer, which is not sequentially the next, just like this one in the example, right? These are not sequentially adjacent, but we pass information between them. So when you do this kind of stuff, which breaks the linearity, the serial nature of the network, they are called combination layers. Using combination layers actually make a network non-sequential, which we also call DAG, directed acyclic graph. So it is a graph, it is directed because the edges flow in one direction. When we say the direction, we are talking about the forward pass, the information flow. And it's acyclic. Acyclic is important because we don't want the information to create a loop. And in deep neural networks, we don't do that. The information in deep neural networks is like a black box. You forward the information, it passes in the graph in a directed manner, and it reaches the end. Actually, that's why deep neural networks are quite well suited for FPGA implementations. It's just side information. You don't know what an FPGA is most probably, but FPGA is a type of hardware design environment where you can implement directed acyclic graph information flow in a very fast manner, whatever. So what kind of combination layers we can talk about? There are different ways to combine split layers. Are you going to split the features themselves? Are you going to send the index value just like we did in the previous one? So what information are you going to send from that layer, from the previous part to the part which lies in deeper in the network? Which information? So depending on that nature of the information that you send with these combination layers, the type of the combination layer also changes. And when you send that part, what are you going to do? If it's an index value, okay, you're going to use the index. If you're sending the exact feature values, what are you going to do with them? Are you going to add them? Are you going to multiply them? Or are you going to concatenate the vector to make it bigger? How are you going to concatenate the vector in the depth dimension or the spatial dimension? So it depends. Are you going to split? So when combination layers combine different parts of the network, we usually call them a skip connection. So this type of thing is a skip connection because we are skipping these parts of the network and combine it. Okay. And when you do a skip connection, actually you can just combine the information here in different manners. For example, in UNet, what they do is, we're going to cover in the practicum session, you have this actuations, which is, for example, if it is n by 32, you send all the actuation values, the actuations themselves. So the input to this network is also sent here and is concatenated in the depth dimension. So here you have this blue part, this part, n by 64, and you have n by 32, which makes a total of n by 96. So you send it and concatenate it in the depth dimension. So it is like you're providing that channel as well. So when this channel, this is a 1-by-1 channel, convolutional network, when it convolves the the depth channels coming from here and here, it creates a higher level feature, which uses the low level features as well. Remember, the features that you have here are kind of low level features like edges and stuff. The features you have here are very large level concepts, like, I don't know, the trees or the vegetation you take from a satellite image. That I'm giving the satellite example because the images in the example is like a satellite example. So you combine that low level features and high level features and concatenate them. So this layer convolves them. It gets higher level representation. Why would I need this? If I'm trying to segment the parts where there are trees, for example, which is called semantic segmentation in tree semantic segmentation for trees, I'm using the high level features which lost their localization because they went through some downsampling. But I'm using the low-level features edges as well to correct the localization, to properly localize them, to define their borders properly, giving them the edge information. So that's a kind of connection that we use in UNet, for example. We're going to cover it, don't worry. I'm trying to prepare you for that practical slowly. What other types can be? You can add the values here, or just like we saw in SegNet, SegNet is another type of semantic segmentation network, which is another paper, where you only send index values. You can also do that. You don't send the values, but you say which specific part was chosen when you're upsampling, so that the high level feature will be localized in that part using the index information. So when you're doing an information flow job, which is different than the information flow defined, which changes the information flow, we skip some part of the network. These are called skip connections and combination layers. Okay. So let me go over it. Okay, so this was the combination layers. So and I continue with the input layers, guys. Input layers. You know what an input layer is, because we've seen it, we talked about input normalization. These are the first layers of a neural net. They're kind of special because you need to shape the distribution of the input to help the optimization process. We feed our signal, data, whatever, to this layer. And when it comes to convolutional neural networks, the thing that you feed is a signal, and it has strong spatial dependencies like an image or a sound. That's why there's a couple of pre-processing stuff that you might be able to do, which comes from image processing or sound processing literature. So input layers do not change this input size because they are the input layers. What they do is normalization or pre-processing. They don't change the spatial size. They kind of transform the input for the network for better training or processing. The purpose of these layers are some sort of pre-processing or transformation, depending on the problem. I mean, the type of pre-processing we would do in an image is maybe normalization or, I don't know, any image processing stuff, but for a sound signal, it's going to be different. In the type of networks you're going to work with, if you're going to work with a convolutional network, whether it's a sound signal or an image signal, most of the time what you're going to do is a zero mean or unity variance. So what is a zero mean normalization? We are going to talk about this next week when we are talking about training and optimization in detail as well. You have a training set. The training set values are pixel values if you're working on a vision system. And they are all positive real values, which makes your first layer's input all positive. Actually, in this case, the input to the second layer, most probably it's a convolutional layer, because in a vision-based deep learning system, after the input layer, usually you have the convolutional encoder, which starts with a convolution layer. Input to that first convolution layer will be positive values that comes from the image, if you do no pre-processing, of course. Is this something bad? Actually, this is something bad when it comes to optimizing or training that system. Why? We are going to talk in the next week. We're going to talk about it in the next week. What people usually do is they normalize. What normalization means? You have a training set of thousands, hundreds of thousands, millions of images. You take an average image. What they do exactly is they put every image on top of each other, the pixel values corresponding to the first pixel of each image, the second pixel of each image, the first pixel of the second row of each image. They take the average and they get an image. It's a strange image. It's like a grayish image, which is more like colorful in the center. So it is like towards the edge of the image, you have all colors most probably. So that's why grayish, it's grayish, because I've seen what is the average image of VGG and Alex Navis. Towards the center of the average image, it is still gray, but it is a bit sense of color as well. Most probably when we take a picture, at the center, we have a colorful contrast component, like a person and stuff. So that's like a grayscale. So what would that meaningless image do? What you do is you subtract that average image from every image in your training set during training. You do this in testing as well. So the values that you feed to the first layer, the first layer of the convolutional encoder, which is the second layer of your network, will not be all positive. They'll be distributed positive and negative, so just zero-centered. This is called zero mean input normalization. Okay, we are going to talk about this in detail. Why? Normalizing the input signals around the zero mean speeds up the optimization process. Now I'm not going to get into much details, but next week we are going to talk slightly about it. It will give you an idea. And this normalization will allow us to create faster optimization and higher learning rates. We're going to talk about it. So this is your original data, because this image, when you're dealing with an image, each pixel is a separate dimension, presumably. So to understand it, this depiction is done on 2 dimensions. So it's like a 2-dimensional data, x1 and x2. However, this CFAR is 30, this is CFAR data set, 32 by 32 by 3. So it's like 3,000 dimensions, but this is 2 dimensions for visualization. So this is the original data. This is zero-centered data. So you calculate the average of each dimension, which is something like here. You subtract each value, from each sample, you subtract this center value, and your data becomes zero-centered. Or you can normalize it as well, which means the distribution of the data in each dimension will be equal. You can do this by dividing each dimension to the variance of that dimension. There are other ways as well. I mean, if you want to decorrelate your data, which means you want not the dimensions you have, but independent dimensions, no correlation between the axes, you do this. And if you need, this will give you a diagonal covariance matrix of data statistics. People will understand this better. And if you just normalize that decorrelated dimensions, it's called whitening the data. In vision, we don't usually do this. But in different types of signals, for example, in time series and other types of analysis, we may need whitened data. So just like I told you, the nature of the input layer depends on the type of the signal. Okay, enough information about input layers as well. Output layers, this is the final layer, in contrast to the input layer. This is the last layers. They decide on something. So depending on the type of your problem, what they decide will change. Before this layer, you have a score function, which is quite highly correlated with the decision that you are trying to make. For example, if you are trying to classify among 10 categories, you have 10 scores, and the category of the score of the category that the right category belongs to will provide higher score if it's a, properly functioning network. So they are higher correlated, but the last layer shapes these scores accordingly. If it's a classification problem, you convert the score functions to a distribution, probability distribution, just like softmax does. However, if it's a regression problem, you normalize or limit the score function to a value which is presumably the dynamic range of the value that you're trying to estimate. You are trying to estimate a probability, a single probability, for example, not a probability distribution or a value or the, I don't know, it could be anything. It doesn't have to be a probability. Maybe probability was another good example. If you're trying to estimate the weather by different values, then you would get a value like 3.1 Celsius degrees. Then it would be a layer to shape the score function such that it will provide you the necessary value. Okay, it could be the score function as well, depending on how you train the system. So this is the output layer. And finally, the utility layer. These layers are quite a bit important. I'm going to be talking about them in detail because these layers also existed in AlexNet, but we omitted them. Utility layers are utilized for only training to start with. So these are the type of layers which we have in the network during training. So they help the information flow for training. So in training, we have the forward information flow and the backward information flow, which is roughly something you already know, but which you're going to cover tomorrow in labs and next week in classroom as well. So during this training information flow, back forward propagation and back propagation, there are certain layers that are used to make the training more functional or optimized. So when the training ends, we take out these layers or we leave these layers in a minimal fashion. What does this mean? I'm going to be talking about two of these, the dropout and batch normalization, because they existed in AlexNet and which is going to make sense. Dropout layer is something very simple, guys. Actually, it's a type of regularization. Remember what a regularization was? Regularization was, as we learned in the previous lectures, was a component in the loss function, which we used to not to suffer from overfitting. So we have put that value. It was like a value added to the loss function. For example, the square sum of the weights added to the loss function so that the weights will not go crazy, because when the weights go larger, the loss function will increase. So the loss function will push the weights to go lower during backpropagation and training. The reason for regularization was to prevent the network from overfitting. That was what he said. Dropout is the same. It is not a value added to the loss function. It is a layer. However, the reason why we use this is still the same. It is to prevent the network from overfitting. How it is done? Imagine this, look at this figure. In the forward pass, what you do is, for example, in AlexNet, you have convolutional layers, and in the end, you have fully connected layers. So before the first fully connected layer, by the end of the last convolutional layer, we have some activations. It is like the output of the convolutional encoder of AlexNet. What you have there is a bunch of high-level features obtained from different parts of the image. So each node has a receptive field, that activation layer, just after the convolution layer, before the fully connected layer, the activations. They have a receptive field that touches some part of the image. And those activations, since this is a deep neural network and we are at some deep part of the network, the last layer of convolutions is quite deep enough, I guess. They provide high-level features, we said. So an activation there would mean that from that part of the network, I have a cat tail. If that filter was a high-level representation which detected cat tails, the tail of a cat. Another part of it, cat face. Another part of it, I don't know, cat feet or cat mustache, imagine. So in the decision part, the fully connected layer, getting all that information, would decide, oh, there's a cat tail, there's a cat mustache, I think it's a cat image. It would say, right? What we do in dropout is, during training, we randomly cut some of these connections. We dropped some of these connections. So while the network is training, it was without the dropouts. What it was going to do was cat tail, cat face, cat mustache, cat feet. It's a cat image. It would have said. When you randomly drop some of these connections in the fully connected layer, the decision would be like some of the features would not reach to the fully connected layer. So instead of deciding like cat tail, cat face, cat mustache, cat feet, it would decide something like cat feet and cat mustache. It must be a cat layer. What is the good side of it? For example, you trained your network with a cat, and during training, you had all these features. So your feature encoder can construct these features. However, there came a test image where the cat is occluded. Occluded means it's behind some thing. I don't know. Behind the cat is on the table, for example. There's the cat. She's behind the glass or whatever. You can only see the feet and tail of it. If you've trained your network with this capability to learn that cat with only a limited number of features, for an occluded version in the test, you would be more successful. So it is to overcome this overfitting problem, overfitting to many features. So when you do this, has ear, has tail, his fur is close. Even some of them are dropped, the cat score will properly be constructed by your network. So it is like you're pushing your fully connected layers to decide with less information. So it is like you're making a primary school student study and you're just not showing every feature. So trying to train it. So this is the dropout layer. That's why it's a type of regularization. You are trying to prevent the network to overfit high number of features. Okay. Okay. So in training, we randomly drop the features. What do we do in testing? Do we randomly drop the features? We don't, because it is meaningless. I mean, maybe the only features that you drop during test is the feature that you need. We don't do that. However, think of this as an information flow. During training, for example, you have cut half of the features. The network was trained by an information signal, which was half of the flow. So during training, what you do is if you've dropped half of the nodes, in testing, you multiply every actuation with 0.5 so that the entire energy of the information flow is halved. Because the feature values are important, but the total information flow is also important. So in testing, we don't do any drops, but we multiply every actuation with the probability of the dropout. Because if the probability of the dropout in training was 0.5, which means you have dropped half of the connections in random, what you do is you multiply the actuations in testing by 0.5. If the dropout was 0.75, you've dropped 3 out of 4 every connection, then you multiply it with 0.75. So during testing interference, the dropout layer is just like a scaling layer for the activations. Any questions about dropout? This is a fundamental concept that you're going to be using in your, especially classification networks.
John, may I ask a question about this? In the dropout layer, how do we deal with the loss function? I mean, since we have lost some of the features, we may increase loss function because we may misclassify some objects, for example. How do we deal with that?
Very good question. Your fan is asking, I'm using the dropout, and what happens to the loss function? I think there are two faults, there are important points that needs an answer with this question. Well, the first one is a theoretical answer. Why we are doing this? What happens to the loss function? What you say exactly occurs. When we drop some of the features, the loss function will increase. Why we are doing this then? Because we are trying to make the problem harder for the network. because it is like you're making some child study difficult material so that it gets better on that subject. So we are teaching the network to get that correct CAT score given less features. Otherwise, it won't learn that. So it makes theoretical sense, right? Does this make theoretical sense? I'm not showing you everything so that you are learning to estimate, do that estimate in difficult conditions as well. This makes sense, right? Yes or no?
Yes, of course.
Yes.
Yes.
Second fold is more technical. What happens during backpropagation? How do I do this? Okay, I understand it theoretically happens, but how does it technically takes place? What happens is the layers that you dropped in the forward pass are also dropped in the backward pass. The gradient do not flow from those edges. The gradient will only flow from the edges which did not drop, which means the weights connected to those features will only be changed. So it is like if you're trying to make this problem difficult, like you are teaching the system to estimate it's a cat image using only one feature, for example, you are strengthening the weight that connects to that these layers to that feature. So it is like you're making it more powerful. You're making its effect on the scope function more powerful. That's how it technically takes place. So with these two answers, I think it makes sense now, right?
Yes, thank you so much.
So technically what happens is when you drop out in the forward pass, it also drops in the backward pass. It changes the connections of the computational graph and the gradient backward flow. Okay, thank you, very good question. Okay, and batch normalization. Batch normalization is about normalizing the activation values. However, before that, I'm going to delve into very briefly weight initialization, which I'm going to delve in detail in the next week. Okay. Proper initialization of weights is an active area of research. These are some paper names. People are working on that. So it's difficult. Weight initialization is actually, what is weight initialization? Weight initialization is before you start training your network, you provide values to the weights of all the layers. What these values will be? Should they all be 0? Should they all be positive? Should they all be negative? Actually, depending on how you initialize your network, your training procedure is dramatically affected, which makes sense because how you initialize your network is actually where you put the blind man in the valley. If you put the blind, because initial position of the weights is the location of the blind guy. Blind guy is just by checking, remember the optimization procedure, checking the slope, trying to find correct place. That correct place is the correct set of weights for the network. So the weight values are actually starting location of the blind guy. If you send him to an absurd place, he won't be able to find his way. He's a blind guy. He can only feel the slope. How to know the proper place about the valley we don't know about, and there's only the blind guy leading us? Well, there are mathematical techniques to this. I'm going to cover it next week, so I'm not going into the details of it, but there are different techniques for different actuation functions. And depending on the actuation function, we provide a different weight initialization value. Okay. So the weights, what I'm talking about here is if the weights are all 0, this will be badly affected and blah, blah. I'm not going to go into the details of it right now. I decided to go into the details of it next week. But when you do not properly initialize your weights, your actuations die. This is a simulation they've done with AlexNet. So when you do not provide proper initializations, what you have is in the deeper layers, your activations die. And actually, when your activations get very close to 0, because of the nature of the gradient descent algorithm and the backpropagation, your gradient also dies and you cannot learn. That's the main thing that I'm going to be talking right now. So there are different visualization techniques and there are papers. the reason that we do a better initialization is to make the training more robust. That's it. That's what I'm going to be defining right now. Next week, we are going to go into more detail. But now it's time to talk about batch normalization. In order to talk about, to be able to safely talk about batch normalization, we needed to understand what weight normalization is, why we need it. Because when we don't properly make the weight initialization, the actuations, as you can see, die. Whatever we do, we cannot sometimes handle this because it is difficult to find the correct starting place for the blind guy, just like I said. In those cases, what we do is we do something called the batch normalization. We are trying to make the actuations do not reach this kind of a zero-like distribution. We want the actuations in the deeper layers to be like this, like Gaussian distributed with a proper standard deviation. That's called batch normalization. Or maybe we should have said it is called batch shaping, because what we are doing is we are normalizing the batch, but the reason why we are doing this is we are trying to shape the batches so that the actuations here will have proper shapes. Okay? The idea is to make the network more stable during training, because just like I said, when you initialize the weights correctly, these actuations get proper shapes. And these actuations get proper shapes. The gradient descent algorithm works better. The gradients will not vanish. So we are doing this batch normalization so that the gradients will not vanish. What we do is we normalize, we apply this function to this actuation. So at this layer, I have an actuation. Okay, I shape it. I apply this function. So it is like if this is a computational graph, I'm adding a layer in between, which is like a subtraction and division operation. When you add a computational layer into the computational graph, which is differentiable, you can still apply forward and the backward pass and the training, right? So it doesn't change anything. It has some parameters. And there are no parameters to learn at this stage. What you do is, at some point of the forward pass, you calculate the mean and the variance, this is the standard deviation because it's square rooted, of the actuations. You shape the network so it doesn't look like this. When you shape it, it's going to look more like something like this. So when you apply this function, it's going to look something like this. Okay? So I have this, and I keep these values so that I use them in the backward pass, because in the backward pass, it's going to shape, these values are going to shape my gradients as well. So there's nothing to learn. There are no learnable values in this batch normalization. What I do is I only change the shape of the activations. And actually changing the shape of the activations help the gradient descent and backpropagation, so the learning procedure, a lot. That's what I do it. That's simple as that. I have activations. I am shaping the activations with these values. I keep these values so that in the backward run, by using these values, the gradient descent is also affected. So if the gradient descent and backpropagation is not affected, the training is not affected. Still, the information will flow in forward and backward propagation properly. And my activations will be properly shaped and my gradients will not die. So this is batch normalization, guys. What you do is you compute the empirical mean, which is the average, and you normalize. We usually insert them after the fully connected layers. Okay? Normalization after the fully connected layers, between the, before the activation layer, so that we have proper layers fed to the activation layer. Because you remember, activation layers are quite fragile to if the value is positive or negative. If it's a ReLU, all the negative values will be dead. But when you properly shape them, because when you have values close to zero, all the activations will be zero for any activation, not only ReLU. But when you properly shape them, we have better values. It is like if I had to resemble it to a mechanism in our neural system. I don't have any technical detailed knowledge of our neural system, but It is like a buffer transformer, like an electrical component before the axon by the end of the dendrit, that connection here, that regularizes the input values like an amplifier. It amplifies the values so that the values that comes to the axon, the new neural cell, are properly processed. Okay. Okay. So that was it about the layers. I'm going to give a break. Then I'm going to show you the UNets, just like I did the previous week using the network analyzer of MATLAB. Any questions about dropout or batch normalization or other layers?